Okay, welcome to my channel. So here with me is McKay, alright? Okay, so we want to evaluate this integral, and the essence of this video is to let you know, alright, that when you have an arbitrary constant, in this case it is a, alright, where it's just any real number, okay, you should be very careful. You don't just do it anyhow. You should be very, very careful, because the result from the integral could be affected by this a. For example, in this case, alright, so you notice that a being a real number, it could be negative, it could be 0, or it could be positive, right? So maybe we want to consider different cases, okay, what a could possibly be. So let's look at the case where a is 0. That is the simplest case, so to say. Yeah, it is going to be. Look at this. If a is 0 here, 0 times x for all x starting from 0 and approaching infinity, alright? Okay, so you notice that when a is 0, you notice that we are going to be having e raised to the power of 0, which is just going to be 1. 1 plus 1 will be 2. That is, we are going to be integrating 1/2. Okay, so integrating 1/2 with respect to x would just be 1/2 times x. So in fact, let's just look at that as case 1, right? So the first case is when a is 0. That is when the little a is equal to 0, right? So I'm saying that the integral will become the integral, right, from 0 up to infinity of just 1/2, right? And then we are doing that with respect to x. So integrating 1/2 with respect to x, you are going to have 1/2x, okay? And we have to take this from 0 up to infinity. So when we substitute infinity, like what we really mean there is, as x approaches infinity, all right, 1/2 times x approaches infinity, and then we subtract, well, when x is 0, we just have 0. So everything here will become just infinity like this. And since this is infinite, that means that this integral diverges when a is 0. The integral diverges when a is equal to 0. So that is it. So in fact, I would like to clean this little work here and just write case 1. When a is 0, the integral diverges. Okay, so we have divergence. So let me just say the integral diverges, so we will understand that. All right. Okay, maybe if we give this integral a name, maybe we call the integral I. We will say I diverges. So I diverges, right? Okay, that's nice. That is the case 1. So you want to consider the second case, the third case, or if at all we will have, or maybe we will need. So let's talk about a case where a is not equal to 0, all right? Let me do it over here. This place, I'm going to reserve it in case I need to do some working. Okay, so let's look at another case. Let's say case 2. Let's say when a is non-zero, all right? And when a is not equal to 0. Okay, so what does that mean? Well, that means this integral, this place is non-zero, so it's not going to be as easy as the first case, all right? Okay, so let's see what we have from there. Well, let's look at this, that we can make a u sub. We can say let u be, well, trying to make this u sub, I had to, do some trials, and I've discovered this, and this one works. This substitution works. We make u to be the whole of this term here, e to the power of ax, all right? We make u to be that, we differentiate that, we have du to be, well, when we differentiate this, we're going to have ae to the power of ax, and then we put the dx over here. All right? So that means we can write this integral as the integral, okay? This is 1 dx. Maybe we need ax, so maybe let's just replace everything anyway. So let me just put the 1 over here. We divide this by 1 plus e to the power of ax is written as u, all right? We call that u, and then we put the dx. Dx is going to be du over ae to the power of ax. So let me put it there. Du over a times e to the power of ax is what we call u, all right? So that's going to be a times u. Good. So maybe next thing we'll have to do is to look at the bounds of integral, all right? Notice this is a definite integral. So as x is 0, okay, when x is approaching 0 from the right, what is u getting to? Well, as x is approaching 0, the whole of this is approaching positive 1. So that means you're going to have 1 here. And then as x is approaching, let me put this in blue. As x is approaching infinity, it's positive infinity, right, here. Let's see. Well, when x approaches positive infinity, let's look at the exponential function, how it behaves when x approaches infinity, all right? Or let's say when the exponent approaches infinity. So e to the power of ax? Well, it depends whether this place will be positive or negative. For example, if the exponent here is a negative real number, all right, the exponential function goes like this. Okay, it's cut here at y equals to 1. And if this place is positive, it grows. Okay, we have a growth as we approach infinity towards the x-axis. But if the exponent is negative, as we approach infinity, this thing breaks down to 0. So what that tells us is that the value we get here will depend on whether this place is positive or negative. We know that x is approaching positive infinity, so the values of x will be positive throughout, right? That means that the thing will be determined or will be decided by what a will be. So if a is positive, we are going to be having a growth, and if a is negative, we are going to be breaking down to 0. So that is it. So you need to always consider a. Don't be very careless about it, all right? So in this case, we would like to say, okay, let's consider another case. Maybe under this case too, we want to consider when a is bigger than 0, right? So we are going to consider this one first. So when a is bigger than 0, take note, this is going to be positive. Now, as x approaches infinity, this will be approaching positive infinity, because when the exponent is positive, okay, we are having a growth, right? So it will be approaching positive infinity. My infinity is not really that good. Anyway, all right, so let's see what we have. So this becomes the integral. Well, we can put this 1 over a out front, okay, since it's just a constant and it is positive, okay. We have the integral, well, from 0 up to infinity of, notice that here we are going to have 1 over u times u plus 1, right? After taking the a out. Okay, so we have to decompose this into its partial fractions. So I'm just going to put the factors down here. You know, they are just linear factors. So that tells us that each of these numerators will be just constant, right? Okay, so to figure out the numerator for this first fraction here, notice that this is u. Well, this denominator will be 0 when u is 0. So we come over here, cover up that u, that is using cover up method, substitute 0 wherever you find u elsewhere, all right? So we're going to have 1 over 1, which means the numerator here will just be 1, all right? And then we do a similar thing here. When u is negative 1, this denominator will be 0. You come over here, you cover up that particular factor, u plus 1. You substitute negative 1 in place of u. 1 divided by negative 1, that will just be negative 1, right? Good. So we've decomposed this into its partial fractions. So that means this place we are going to write it as 1 over u, okay, then minus 1 over u plus 1. And then we put the du over here. Okay, that's nice, isn't it? So let's see. This will become, well, let's put 1 over a out here. Well, when we integrate 1 over u, we're just going to have natural logarithm of u, right? And then from 0 to infinity, so 0, did I say 0? Sorry, it's from 1. Okay, notice that when x is 1, u will be, when x is 0, u will be 1. So yeah, this is from 1. This right here is from 1. Okay, this right here is from 1. Okay, I don't know why this thing is not writing well. Something like that. So when x is 0, this place will become 1. So the lower bound is going to be 1. So we take the natural logarithm of u from 1 to infinity. So it's positive. There's no need for the absolute values. All right. And then we take minus. Well, the natural logarithm of, this is just u plus 1. So you put the u plus 1 here, and we have to take this from 1 up to infinity, right? Okay, great. So you notice that when we substitute infinity, that means as u approaches infinity, natural logarithm of u approaches positive infinity, and the natural logarithm of u plus 1 also approaches infinity. So what we have here is infinity minus infinity situation, which is an indeterminate form. So we need to, you know, do more work on that, okay? Because we're taking limit as u approaches infinity. Okay, but also notice that when we substitute 1, which is the lower bound, okay, we are going to have, this is 1 over a out here. So let me keep this space for when we approaching infinity. Then when we are substituting 1, we're going to have natural logarithm of 1, which is just going to be 0. Then minus, well, natural logarithm of 1 plus 1 will be 2. So that's natural logarithm of 2, right? Okay, so let's see when u approaches infinity to see what we have. So to rewrite that, I'm going to rewrite it as natural logarithm of, you notice that we are having natural logarithm, the difference of the natural logarithms, which will be natural logarithms of the ratio, okay, of these two. That will be u plus 1, right? I take note that we have to take this as u approaches positive infinity. Well, now notice that to solve this kind of stuff, okay, we usually start by dividing both sides, or dividing numerator and denominator by u. All right, let's see if that will work. So we divide the numerator by u, and then we divide the denominator by u. So you notice that when we divide u by u, we're going to have 1 at the top. Okay, we divide u by u, we're going to have 1 here, and then we're going to have 1 over u here. So as u approaches infinity, this will become natural logarithm of 1. The 1 will just stay 1 here, and then 1 over u. All right, as u approaches infinity, 1 over u approaches 0. So this is natural logarithm of 1 over 1, which is going to be 0. Natural logarithm of 1, which is 0. All right. The reason why this works is because this natural logarithm is a continuous function, okay, whenever for all positive inputs. So since it is continuous, we can switch between the limit and that. So we can get inside the function, all right? And when we do that, we're going to have 0. So that tells us that as u approaches 0, this difference approaches, as u approaches positive infinity, this difference approaches 0. So all in all, we are going to have 1 over a out. Then we have negative of this. That will be positive natural logarithm of 2, all right? And this right here is the result when a is positive. Take note, when a is greater than 0, all right? Okay, so we still have one more case to consider. Let me see if we can fit in everything here. And that is when a is less than 0. So let's look at this. When a is less than 0, we're going to have the integral, okay? Well, so you see that using this u sub, okay, let me put it down here. When a is less than 0, so we say when a is less than 0, all right? Okay, so this is going to be the integral. Well, as when x is 0, okay, u will be 1. Of course, that is it. When x is 0, u will be 1. And then when x approaches infinity, given that a is negative, that is less than 0, okay, the thing will be approaching 0. So you observe that. Okay, great. That is the limit as x approaches infinity of u, where u is e to the power of x, where a is less than 0. The thing will be approaching 0. Okay, and we put the function down, which is 1 over u times, let me put it in black, 1 over u times, right, u plus 1, okay, and then we are going to take the a out front. So let me put the 1 over a outside here, and then you put the du over here. Of course, we've already done this. That will give us 1 over a times the integral from 1 up to 0. Though this is not really good, right? Maybe we can change the bounds by multiplying both sides by positive 1. So let's see. By decomposing this to partial fraction, we're going to have 1 over u minus 1 over u plus 1, okay? And then we put the du over here. Okay, that's nice. Anyway, so let's see. When we integrate this, we're going to have 1 over a, okay? And then integrating this will become between 1 and 0. Anyway, let's just put it. Natural logarithm of u, right, minus the natural logarithm of u plus 1. Okay, so we have to take the limit here as u starts from 1 up to 0, right? Okay. Anyway, this is not really a good one, so maybe we can multiply this by -1 and also change the bounds. So when we do that, we are going to have 1 over a, multiply this by -1, okay? That will help us to switch the bounds. That means we are going to have 1 over a into natural logarithm of u plus 1, because I'm multiplying by -1, minus the natural logarithm of u, okay? So we can take this from 0 up to 1. And this is now very nice, all right? So we'll be looking at the as u, when u is 1 and when u is approaching 0. So let's see what that will give us. Oh my god. Okay, so when u is 1, we have natural logarithm of 1 plus 1, which will just be natural logarithm of 2, all right? Okay, so that is natural logarithm of 2. Then minus, well, when u is 1, that will just be -0. So we are done with that part, and then we are going to be looking at when you approach 0 from the right. So that will be minus. Well, natural logarithm of 0 plus 1 will just be 1. So natural logarithm of 1 will be 0 minus. Well, as you approach 0 from the right, okay, take note, this is the 0. Well, natural logarithm of u will be approaching negative infinity. So we're going to have negative infinity, right? And of course, this is not good, right? This is not good. So negative will give us positive. Well, natural logarithm of 2 minus a positive thing, that will be natural logarithm of 2. Natural logarithm of 2 plus, minus infinity, right? Minus infinity. This is negative infinity multiplied by 1 over a negative number. That will become positive infinity, which means that this right here diverges. So that tells us that this integral here, okay, only exists when a is greater than 0, and that is the result. But when a is either 0 or less than 0, okay, the thing diverges. It diverges. So you note that, okay, that the how do you call it, the arbitrary constant can actually affect the result of our integral. Okay, that was nice, isn't it? All right, thanks for watching, and please subscribe to my channel, share this video with your friends, and I'll see you in our next video.